Okay, Newton's second law lab. So, right after this, there'll be a video showing the setup of the lab. I'll sketch it out here and just talk a little bit about how we collected this data. And then I will make a second video, which will be dedicated to the evaluation of data for this lab. Now, this lab is done in Physics 11H typically. And my students in Physics 11H will do this lab and have done this lab. But some of you haven't done this lab, and it's worthwhile doing this one to really kind of focus in on the relationship between net force and the acceleration of a system. All right, so what we have in this lab setup is a track with a card on it. All right, so we set the track up in a pulley. All right, we set the track up so if I give the cart a little push, it moves at a nice constant velocity without any extra, without mass hanging from it, right? But the reason we do that is because we want to cancel out any effects due to friction, right, on the wheels. If it's perfectly level and you give it a push, it'll actually slow down and stop, well, because friction. So we want to mitigate any effects due to friction. So we actually get the track set up on the table, and we raise the back a tiny little bit using the feet of the track. So again, I give it a push without any weight tied to it, and it just goes at a nice constant velocity. So what we do is we take a motion detector, put it on the end of the track, right? And we hang mass off of it and let it accelerate. So, one thing that's important is that we have to measure the mass of the system. All right. So, the system is whatever's moving here. So the mass and the hanging mass and the cart together make up the system. This is all accelerates together. The string that connects these two things ties them together, much like a molecular bond ties together any solid. It's part of the accelerating system. In fact, if I had a chain or something, I would have to keep track of the mass of it. The string here doesn't have much mass. The pulley also has rotating mass. We're not going to factor that in. We're actually going to add some mass to the cart to make it heavier so that when we let it go, it just doesn't go flying off the end of the track. It gets fast enough as you add mass here. And you'll see something in the video. What I do is the brass masses that hang off the end, I actually take, I put them all on the cart first, and then one by one I move them over to the hanger, because I don't want to change the overall mass that's being accelerated. So the purpose of this lab, all right, is to determine the relationship between the net force acting on a system and the acceleration of the system. All right, so I'm writing kind of fast here and sloppy in the glare. All right, so determine the net force, the relationship between the net force acting on a system and the acceleration of the system. So, sorry for the glare there. And we achieve that by changing the amount of force pulling down here. The weight of the hanging mass is what accelerates all of this mass. There's other forces here, right? There's a force of tension acting here. There's a force of tension acting here. Those are the same force of tension. They're internal to the system, so they don't count as an external accelerating force. We have a normal force on the cart here, and we have a gravitational force in the cart here, they cancel each other out internally as well. They don't act to accelerate the system at all. So all the acceleration on this whole system, if we think of this as just one big blob of mass, right, moving, all of the acceleration is coming from that little force of gravity. So this force of gravity actually is our net force. All right, and we're going to measure the acceleration. How do we measure the acceleration? Well, we look at the velocity versus time graph. All right. So what we do here, actually I gotta clean this eraser. This board has seen better days. I neglected it for a little. I left some stuff on it and I had to really scrub it to get it clean. So I'll have to clean it a couple times to get it back into shape. But anyhow, we let the cart system go and it accelerates away from the motion detector. When you look at the velocity versus time graph, actually when we did this today, we got really nice data. On the old tracks down in room 213, the velocity versus time graphs always look like this, right? It takes a little bit to break them free, then they accelerate, and when you catch them, they stop. So you always have this little hiccup. Today when we ran this up in 313 with the newer tracks, newer carts, leveled a little bit better, extra careful, they really did just kind of start going up and then stop. So you had a much better graph for this data set. This is pretty cool. And what you do is you find the fit line of velocity versus time, velocity versus time over the range where it's accelerating constantly. All right, put a fit line on there, you get the acceleration. So our data table here ends up looking like this. 3 columns. I do the hanging mass hanging, and it's usually like 0.05 kilograms, so it's in kilograms, kg, 0.07, 0.09, ... up to like 1.3 or 1.5, something like that, 1.5 usually. Some people start off a little heavier. You just got to be careful going heavy because it really starts to go crazy. And then this column, we determine the net force acting on the system, F net, in newtons. Well, that's just this value multiplied by G. Remember I said the force of gravity acting on the system provides the net force to the system. So we just multiply all of these by G. Now, you can do this by hand with a calculator, or you can use Logger Pro and do a calculated column, data, new calculated column. You just take your mass column, multiply it by G. And then here, we measure the acceleration. All right? So you'll see in the next part of this video, the actual lab setup, us collecting the data. And then I will make another video of plotting the data and undergoing the evaluation of data. All right, this is going to prove Newton's second law. One thing you have to do here, and I'm also going to post a video of the raw data or a picture of the raw data I collected. I actually sat down today while the students were doing their data collection, and I collected my own data. I haven't sat down and performed one of my own labs from scratch in quite a while, so it was nice to sit down and do that and, you know, try to model good data collection techniques, you know, for the students so that they do a good job, you know. So I actually measured each one twice, and actually what's kind of cool is they when I did the accelerations twice, they were all pretty much the same as I did it. I actually kind of stopped doing it twice as I went because they kept coming out the same. So I just kind of didn't bother. The mass of the system is interesting. You'll see in the video, the carts themselves, all right, they've got these kind of neat little pockets to hold these little hexagon masses in here. All right, and we put 4 of them. They're kind of like the size of batteries. Each one of those is 125 grams. I think we measured the cart to be 265 grams. And then actually these also have a target that can go on the back of them. And the target helps you get a good surface for motion detecting. Some kids years ago figured that out, that they could get better results if they put a target on the back of it. Down in 213 in the labs, we used to do a lot more labs because it was a lot easier. We could just go to the back of the room. I could have it set up. You know, you could just go to the back, do it, come back. to the front. He worked a lot better, but I think the new lab is, going to work out as well, pretty well, for labs moving forward. Once we get through COVID and we can actually work together, the key there is just making sure the class size isn't too big. So anyhow, 26 grams is what that little shield thing was. We had 125 grams in each one of these, so that's times 4. 265 grams, I think, was the mass of the cart. It's all in the raw data. And then the other thing you have to factor in is how much mass you used, the hanging masses, those brass masses. It's funny, when I make these videos, I always think of alumni, who've used these same masses, thousands of kids by now have used these same masses over the years. It's kind of funny to think about that, but there it is. I think a lot of us used 190 grams or so. So you add all this mass up, right? And that ends up being the mass of the system. You need to make sure you record that and have that, because that's very important when we analyze the data to try to understand what we are deriving. All right, so I'll cover that glare up. Anyhow, just a little introduction to the lab, motivation, purpose, kind of the procedure, and then the next part is a video of the data collection. So those of you that are full remote can pretend like you did it. All right. So the lab here, if you had me for physics last year, we did this lab. We've got the motion detector we're going to use to find the acceleration of the system. We're going to have the cart, the target on the cart, the masses, and these extra masses, and a pulley. So what we're doing here is we're determining the relationship between the force on the system and the acceleration of the system. Okay, so I'm going to get this set up, ready to go. It's all ready to go. I've got all my mass written down, the total mass I'm using here. It's a combination of a few things. I'll show that in another video, I'll maybe splice them together here, the board stuff we talked about. Well, I go over here, hit collect. Here's the motion detector. I let it go, and I catch it. All right. So now, for my data set, I'm going to find the slope of the velocity versus time graph to figure out the acceleration. So I highlight just the middle portion of that velocity versus time graph. I put a fit line on it. And it tells me my slope is 0.5234 meters per second squared. So my data table, the hanging mass is 50 grams, or 0.05 kilograms, and the acceleration is 0.52 meters per second squared. I'm only going to do 2 sig figs on this stuff. I'm going to run that one more time just to be confident. I'm going to hit collect again. Let it go. Stop it. Highlight that again. Put a fit line on it. I got 0.52 again for the slope of that line. So I'm confident that with 50 grams hanging, the slope of the velocity versus time graph ends up being 0.52 meters per second squared. All right. So now I'm going to take 20 grams off of the cart and move it over to the hanging mass. So I'm keeping the total mass of the system constant while changing the force on the system. All right? So I'm going to do it again. You collect here. Stop it over here. All right? You could actually extend the length of the data collection and run it twice all on the same graph. So R equals, I got 0.72 now. So I'm up to 0.07 kilograms. I have 0.72 meters per second squared. Nice. All right.
Oh, Mr. Harmon, why is your stuff falling apart?
Alright, I'm going to try it again. Hit collect, just to be sure. Let it go, catch it. Alright, I'll put another fit line on here. I'll move the bound a little bit. I got 0.72 again, so I'm confident in that result. And I'm going to continue on moving mass over until this thing's going super fast and I can barely catch it. Until I got about 6 or 7 data points. Alright, so I'm changing the total mass in the system. Again, the purpose here is to determine the relationship between the net force acting on the system and the resulting acceleration of the system. Okay, I'll make another little video on a whiteboard, maybe at home tonight, kind of showing what we did in class on the board. Alright? And I'll talk about the different masses of everything that we used, okay? And then, once I get all this data collected, I'll take a picture and I'll send it off to you. There's another version of this you could do at home, actually, now that I think about it. But we'll stick with this for now.